This work is about robust threshold ECDSA with online-friendly design in 3 rounds. I'm Guofeng Chang. It's a joint work with Haiyang Xue. We are both from Singapore Management University. Let's start with some background about threshold signatures. A signature scheme is a public key, a crypto primitive. Private key is used to sign, and public key is used to verify. The security of a signature scheme is equal to the safety of private key, or called secret key. How to protect the private key is a very important topic. And the threshold signature can do it. Where private key is shared among several parties, any T+1 parties can sign, but T parties cannot. The T is the threshold value. For example, if T is 2, any 3 parties can sign, but any 2 parties cannot. The threshold signature can provide a high-level private key protection. Why we talk about threshold ECDSA? ECDSA is a standard signature issued by the National Institute of Standards and Technology. It's NIST. It has been widely deployed, for example, in Bitcoin, Ethereum, TLS protocol, etc. Especially in cryptocurrency, threshold ECDSA is very popular because ECDSA is used to sign and verify transactions. The people who own the secret key are the people who own the Bitcoins or the money. If secret key is lost, the money is lost too. It also has the problem of single point failure. But all these problems can be solved by threshold ECDSA. It has been used in industry like Zingo, Fireblocks, BitGo, Coinbase, many fintech companies. In academy, there have been many constructions, which can be mainly fall into 2 directions. The first direction is to improve the security. The basic security requirement is security with a bot. The protocol may abort due to malicious parties' misbehaviors. The stronger security requirements is identifiable bot. It allows for the detection of misbehaving parties after a bot. The strongest security requirement is robustness. It's also called GOD in generic MPC field. GOD is guaranteed output delivery. It can guarantee the success of each signing execution under honest majority assumptions. The other direction is to improve the efficiency. One measure for efficiency is the number of communication runs. It's a very important factor to influence the network latency. The other measure for efficiency is the online cost. For threshold ECDSA, we see the signing protocol is online friendly if the online phase requires only elliptical group operations, which is much cheaper than other operations like homomorphic encryption or decryption. We use recent constructions to exemplify the state-of-the-art of this field. DKLS24 is round minimal. It's 3 round and online friendly. But it can only achieve security with a bot, not identifiable bot, not robust. CDKS24 in crypto can add identifiable bot. And it's also online friendly, but it requires 7 communication rounds. WMY plus 23 is the first robust game, and it's also online friendly, but it requires 5 communication rounds and 2x rounds for cheater identification. WMC24 is also a robust scheme. It requires 4 communication rounds, but it's not online friendly. In this paper, we give a 3-round robust game. It's also online friendly, which means our online phase requires only elliptical group operations. Our technique can be shown in high-level ideas. ECDSA is to compute sigma, where k, gamma, x are all shared secret values. X is assigning k. K, gamma are both secret nonce. For robustness, previous robust threshold ECDSA requires all secret values are shared using Shamir secret sharing, and use MTA as a basic tool to process k times gamma and x times gamma. MTA is a 2-round protocol. In first round, gamma is used. In the second round, k and x are used. Using previous techniques, it requires at least 4 rounds. Because before running 2-round MTA, we use X round to share k, gamma, and x. So the offline requires at least 3 rounds, and online requires 1 round to open share. So it's at least 4 rounds. In this paper, we use undetermined gamma. The gamma is undetermined. So we don't need an X round to share gamma before running 2-round MTA. And because k and x are only used in the second round of MTA, so the sharing of k and x can be run together in the first round of MTA. So the offline requires 2 rounds in total. Adding the online phase, the entire protocol for signing is 3 rounds. We are the first 3-round robust game. Also, for robustness, we need to identify all misbehaving parties to publicly kick them out. In the offline phase, we construct IMT with public checking, where public checking is necessary, because we find a vulnerability of previous WMY plus 23's robust scheme, which uses MT without public checking, so public checking is necessary. We use the zero-knowledge proof added to previous 2-round MTA to construct a 2-round MTA with public checking. The proof can be aggregated in multi-party cases. In online phase, we construct an efficient DDH relation zero-knowledge proof over elliptic curve. It's online friendly because it's very fast compared with other operations. It really requires only elliptical operations. As another contribution, our techniques of adding robustness can be extended to construct threshold BBS plus with robustness. Finally, we compare our work with the previous 2 robust games. They are WMY plus 23 and WMC 24. Compared with the work in 2023, our protocol, signing protocol, is only 3 rounds, but theirs requires 5 communication rounds. And ours is more efficient for both offline and online phases. And compared with the work in 2024, our signing protocol requires 1 less communication round. And our online phase is significantly faster. For example, in 2-party setting, their online phase requires 308 milliseconds, but ours requires only 0.5 milliseconds. So we are much, much faster. On the other hand, our overall cost is superior only in small-scale cases. Actually, these cases are more common in practice. Oh, that's all. Thank you.